session. Okay, so let's go to so this week the topic was about compressible fluids. So a compressible fluid is a fluid that when it undergoes a change in pressure, it also reduces its or increases its density. For example, air, gas, steams. When you, if they are under pressure, the density of these fluids will increase. So that's compressible flows. In majority of the problems, we don't need to consider the equations related to compressible flows, but in some cases, particularly at high velocities, at high speeds, we need to consider some different equations. We need to treat the fluids in a different way. And this happens when, especially when the flow is close to the speed of sound speed. So that's why we use the Mach number, which is a relationship between the fluid velocity to the sound speed, the fluid speed to the speed of sound, sorry. Then I think above 30% of the speed of sound, we need to consider these different formulas, different equations, because then the compressibility of the fluid is important in the way this structures behavior. Okay, so we to calculate the speed of sound, which is like a kind of a property of a fluid, because each fluid has its own speed of sound. For example, air differs from water, differs from other gases, and that depends on temperature, depends on I think a specific heat ratio, and R is a constant. So basically, it depends on temperature. Okay, and this K here is a property of the fluid. The temperature is another like a state, and R is a constant. Okay, now when the Mach number, which is the ratio between velocity and the speed of sound, this is or it represents the percentage of the flow in relation to the speed of sound. So if we say that fluid has a Mach equal to 0.3, for example, it means that it's traveling at 30% of the speed of sound, which is the maximum speed achievable by that flow. So when Mach number is below 30% of the speed of sound, below 30% of the speed of sound, or when Mach is below 0.3, the flow can be regarded as incompressible. When it's above 0.3, then we need to consider compressible flow conditions. So Amir talked about a lot of different equations that for compressible flow, and they all use the Mach number as input. Okay? So you can calculate temperature, pressure, and other things based on Mach number. So I think I'm just gonna skip this part here, and I can explain that later if that becomes relevant in these questions. Okay, so the first question is the velocity of propagation of sound is calculated by assuming the process is isentropic. Isentropic means that the process doesn't receives external energy, it receives external heat, or doesn't lose heat, and there's no friction. Now, what's the velocity of sound at 80 degrees Celsius? So as I said before, the speed of sound is calculated by this formula here. Okay, so we need to enter this K value, which is a specific heat ratio, which is something particular to each type of fluid and also depends on temperature, that K value. Sorry, I don't think it depends on temperature. I think it's a fixed value. And T is the temperature, and R is a constant, always the same value, okay? So the specific heat ratio for air is constant and equal to 1.4. This R value, which is called the gas constant or universal gas constant for air, is this one, this value. And the temperature here needs to be entered in Kelvin, okay? So you take the temperature in Celsius and add 273 to get the temperature in the Kelvin scale, okay? Now apply the formula and then you get the speed of sound for that temperature and for air, okay? So that's a very simple one. Here is all the properties where you can see that you can see the R value, okay, the gas constant, which is actually the gas constant also relates to the type of fluid. The K value here is also, as you can see, it relates to the type of fluid. So you can get all these properties from this table here. And in our example, we used the fluid that we were working with was air. So we used this value for R and this one for K. Okay. Can I move on to the second one? Okay. Sorry, I just have one screen, so I have to keep switching between my PowerPoint and the Blackboard screen. So we've seen this already. Okay. Number 2. During a storm, lightning can often be seen to strike the ground before the accompanying thunderclap is heard. If an observer measures the lightning strike and the thunderclap to be 5 seconds apart, okay, so we have 5 seconds between the light and the sound. How far away is the storm from the observer? And that's for a temperature equal to 32 degrees Celsius. So basically, we're going to apply the speed of sound here to check how distant this storm is from the observer. And the fluid is air, so we need to convert that to Kelvin by adding 273. We have the time of travel, which is 5 seconds. Some assumptions: air is an ideal gas, so that means we can apply that formula for the C value for the speed of sound. Lightning is seen instantaneously. That's like basically there's no, like, we don't need to consider the speed of light. The distance covered, we will call it D, which is what we need to find. Okay, so we know that velocity times time is equal to distance. Okay, so that's this part here. So distance is equal to speed times the time. So we need to find the speed of sound and then multiply by 5 seconds. To find the speed of sound, apply the speed of sound formula with K equal to 1.4, R equal to 287 joules per kilogram per Kelvin, and 305 is the degrees Kelvin. Sorry, temperature in Kelvin. From here. So the speed of sound is 350 meters per second multiplied by 5. That equals to 1,750 meters or 1.75 kilometers. Okay. How long does it take for the light to travel? Okay, so that's probably another question which was not part of the problem, but just out of curiosity. If you want to know how long it takes for the light to travel that distance, then you can apply, just use like a velocity of light, which is approximately 300,000 kilometers per second, and then you divide the distance by the velocity, and you'll find the time, the travel time. And that's why, just to show you that the assumption, this assumption here that lightning is seen instantaneously is valid, because that's just like quite instantaneous, that time that is calculated here. Okay. Can I move on? Okay, thank you. Now back to my PowerPoint. Done. Okay, next one. Calculate the skin temperature of a civil aircraft cruising at 10,000 meters. The temperature is negative 50 degrees Celsius and Mach is 0.8. So Mach allows us to calculate the speed of the aircraft, the skin temperature, that will be the temperature of the outside of the airplane. This part here for the problem is, I think it's just like an example of what happened once, or like what usually happens is that when this Concorde aircraft, which is the world's only supersonic passenger aircraft, the skin of this aircraft sometimes exceeds 100 degrees Celsius because of the velocity. Okay, and then this aircraft could achieve Mach equal to 2. So that means 2 times the speed of sound. And that temperature of 100 degrees was reached even if the ambient temperature, the temperature of the surrounding air, was negative 60 degrees. It's because of the high speed of the fluid in friction with the skin of the airplane. Now, this question also asks you to use Excel to plot the ratio between skin temperature and ambient temperature as a function of the Mach number. So I'll do this one later. Let's do the first part first, which is to calculate the skin temperature of this aircraft under this ambient temperature. So ambient temperature is the temperature of the fluid surrounding the object, and the object is traveling at this Mach, which is the same as saying that the fluid is traveling at this particular Mach number. Okay, so in this case, the fluid is the aircraft that is moving, but it's the same thing. We can say that Mach applies to either the fluid or to the aircraft. All right. Remember to always convert temperature to Kelvin when it comes to calculated speed of sound. So in this case, we have a temperature of negative 50 degrees Celsius, which is 223 Kelvin. And Mach is 0.8, 80% of the speed of sound. The skin temperature is calculated by this formula here, which considers the ambient temperature, which is the temperature of the fluid around the aircraft, the specific heat ratio and the Mach number. Okay, so you can see here that it's only, the skin temperature is only a function of the speed, which is Mach, and the ambient temperature. So it's very simple equation. The temperature of the air is 223. K is 1.4 for air, okay? Remember that this would be a different value if it was a different fluid. And the Mach number in this case is 0.8. Okay, so that gives us a skin temperature equal to negative 21.5, which if you compare that to the ambient temperature, you can see that it's much hotter. So the skin temperature of the aircraft is hotter than the ambient temperature, which makes sense. So the friction of air on the skin causes that temperature, the temperature of the skin, to increase. And that's not a high increase because the Mach number is not too high. It means that the aircraft is traveling at 80% of the speed of sound, which for this type of aircraft is not too high because, as if we look at the previous example, it said that it could travel up to 2 Mach. And this is what we're going to do in the next part. We're going to check what happens is that if the Mach number is 2. So for that particular case, the altitude was 17,000. Well, that's actually not relevant. The altitude is not relevant. What's relevant is the temperature, okay? So the ambient temperature was negative 60 degrees. That's 213 Kelvin. And the Mach was 2. So the aircraft was traveling at twice the speed of sound. Now apply this equation is called stagnation temperature equation. So apply this equation, and then you will see that using, of course, Mach number equal to 2 this time, you will see that the temperature of the skin is now 110 degrees Celsius. And for the previous example was negative something. Negative 21 for Mach 0.8. And now it is 110 degrees Celsius for Mach equal to 2. And that confirms what's said here in this example. Here that the skin of the Concorde aircraft, the world's only supersonic passenger aircraft, regularly exceeds 100 degrees Celsius. Okay, now then the last part is for us to plot the ratio between the skin temperature and the ambient temperature against the Mach number. So if you look at the equation for the stagnation temperature, you'll see that Ts is equal to T air times this term here. So if we just move T air under here, we'll have the ratio. We will have the ratio Ts over T air. So Ts over T air, which is the ratio that we want to calculate, equals this part here. Okay, so Ts over T air equals this. Then you can vary the Mach number. And here, I just took this from Amir's slides. He used Mach 0.2 up to 2. So that means that as we increase the Mach number, the temperature of the skin gets higher. The ratio between skin temperature and ambient temperature increases. So for Mach 0.2, which means an aircraft traveling at 20% of the speed of sound, the temperature only changes by 1%. The temperature increases by 1%. But when the speed increases to double the speed of sound, there is an 80% increase in skin temperature in comparison to the air temperature, to the surrounding temperature. Is ambient temperature being held constant for this table? Yes. It actually doesn't really matter. What is being plotted here is the result of this equation here, okay? So you have Ts, T air, as a result of this part of the equation. We're not going to use any number for T air to find Ts. You leave this one as an unknown. Ts over T air is your unknown. This is what you're going to calculate here on this column. And regardless of the air temperature, that ratio will be always the same. So if the temperature of the air is 10 degrees, for example, and the aircraft travels at Mach 2, this ratio is still valid, is still 1.8. So that means the temperature of the skin is going to be 1.8 times 10 degrees Celsius. So the ratio found here is fixed. These numbers here will always be the same regardless of what temperature you will be working with. Is that clear, Andrew? Okay. Next one. Just a reminder here to complete the survey. Okay, let me skip this one. Okay. So problem 4. Air flows isentropically through a duct, like in this picture. At entrance, the area of the duct is 0.5 square meters. Velocity of the fluid of the air is 180 meters per second. Pressure is 500 kilopascals. And the temperature is 470 Kelvin. We want to calculate Mach number, the Mach number at this point here, the stagnation temperature, stagnation pressure, and A star. A star would be the area of the constriction, and mass flow rate is usually in kilograms per second, like mass per time, mass per unit of time. That's the mass flow rate that is flowing in this system. Okay, so what will happen here is that the fluid is flowing and it will accelerate. Why is it going to accelerate? That's because the area is getting smaller in this constriction here. Then on this section here, it will decelerate. So velocity is increasing in this direction, then it reaches the maximum velocity here, and then it starts decreasing again. Now, that TT and PT is called stagnation temperature and stagnation pressure, is the temperature of this fluid if this flowing fluid at this speed and at this temperature would be suddenly brought to rest. This would make the fluid increase its temperature, and that's what the TT means, which is the same formula as the skin temperature that we used before. And PT is the same thing, is the pressure of this fluid. If this fluid was brought to rest, what would be the increase in pressure of the fluid? So this was explained during this week in the lecture. So you can refer to Amir's lecture to, I think he went through all these concepts in more detail. So to calculate Mach, so that's the first part, to calculate Mach value. So that's the velocity over speed of sound for that fluid. So let's calculate the speed of sound for the fluid, which is air. So therefore the K value is 1.4, the gas constant is 287, and the temperature 470. Okay, so those values were all provided here. I mean, the temperature was given in the problem. So the speed of sound for this condition, for this temperature, and for this fluid is 434.6 meters per second. The velocity is 180. So now we're able to calculate the Mach, which is the percentage in comparison to the speed of sound. So 180 divided by 434.6 equals 0.41. So this flow is flowing at 40% of the speed of sound. 40%. Now, stagnation temperature. What would be the temperature if this fluid would be stopped, would stop flowing? What would be the increase in temperature for this particular Mach number? So we need to enter the ambient temperature and the Mach number to find that temperature. So that's 470, which is the temperature. 1.4 is the K value, and Mach is 0.41. So the temperature would be 486.1 Kelvin. It's kind of, you can see this as the as sort of the energy in this flowing fluid. So the energy is stored, the potential energy stored in this fluid in terms of temperature. So flowing in this flowing condition, the temperature was 180, but if stopped, the 470, but the maximum temperature that it could be achieved is 486.1 Kelvin. But again, I'm not really sure about this concept, so I really go back to the lectures this week, and Amir probably spoke about the stagnation temperature and stagnation pressure. Now, with the stagnation pressure, which is the same thing, what would be the pressure if this flow would be brought to rest? So that's the state pressure, which is 500, the current pressure. And here is converted to pascals, so that's why it's multiplied by 10 to the power of 3. And here is the 1.4 for K value. The Mach number is 0.41, calculated before. This is this exponent here is this part of the equation. So that equals 562 kilopascals. So when a fluid is brought to rest, it would increase, it will have its maximum pressure because the velocity would be the minimum velocity, and that's called the stagnation pressure. Okay, Now part B is to find the area of this constriction. Now to find the area of this constriction, you can apply this equation here for it's called the Laval nozzle. This type of designs of ducts is called the Laval nozzle, which is like has this converging section, and then there's a throat in which the velocity is maximum, pressure is at minimum, and then we have the diverging section in which the velocity starts to decrease, pressure starts increasing again. Okay. So we can apply this formula here to find this A star, which is the area of the throat, the sectional area of the throat. So if we look at all these terms here, we need to use the Mach number for a given known area. So we know this area here, which is 0.5, and we know that Mach value here, the Mach number for this location is 0.41 that we calculated before. So then for that area and that Mach number, we can find the A star, which is the constriction area. Okay, so using k equal to 1.4, you can get like a simplification of this equation to this one. So for air, this more like complex expression can be simplified to this for air. Then here you just apply the Mach number calculated at area 1, which was 0.41, and the area 1 is 0.5. Then solve it for A star. So the constriction should have an area of 0.32. Okay, now if the constriction has an area of 0.32, it means that at this constriction, the Mach number would be equal to 1. So that means this flow would achieve the speed of sound at the constriction. So this formula here is actually a ratio between the Mach number at one specific area to the Mach number the area at one particular Mach number to the area of a location in which the fluid achieves Mach equal to 1. So this is that place, the place where the fluid achieves Mach 1, where the fluid achieves the speed of sound. And that's equal to 0.32. Okay, now knowing the area required for the fluid to achieve the speed of sound, we can now calculate the mass flow rate that we need to inject here in this system, so that at this temperature and pressure, so that it will achieve the speed of sound at this location. And that mass flow rate is given by this equation here, okay, in which we need to enter the stagnation pressure, the area of the throat, the R value, and the stagnation temperature. So this is why the TT and PT value were important before, so that we could find the flow rate, because ultimately what we need to find is mass flow rate. We need to find the area of the throat for the design of this type of system, this the Laval nozzle. We need to find the design of the system. They involve finding the size of the constriction and the mass flow rate. So we do all these things to find these values. So we found the area of the constriction here, and now we're going to find the airflow rate, the mass flow rate. Okay, so the mass flow rate is 334 kilograms per second. Now, with this flow rate, this temperature, this pressure, and with this constriction of 0.32, this flow, this air, would achieve the speed of sound at the constriction. It's a bit complex. Sorry if I couldn't explain very well, but that's the best that I could do. You have any questions, Andrew? Okay. All right, so let's go to the next one, which is the last one. It is desired to expand air from PT 200 kilopascal. Let me just change the pointer. And temperature, total stagnation temperature 500 Kelvin through a throat to an exit Mach number of 2.5. So we need the Mach value of this, we need the velocity of the fluid here to be 2.5 times the speed of sound. The desired mass flow rate is 3 kilograms per second. Assume the air to be isentropic with K equal to 1.4. Calculate the throat diameter, the exit pressure, the exit temperature, the exit velocity, and the exit diameter. Okay, so here are the given quantities. We have the pressure and temperature. We don't know the size of the throat, so we need to find the diameter of the throat, and also the pressure here, we call it PE, the pressure at exit, the temperature at exit, and velocity at exit, and also exit diameter. Okay. Okay, so because we know the stagnation pressure and temperature, because the fluid is at rest, so we have the total pressure and total temperature. So we can calculate the mass flow rate. Sorry, the mass flow rate is, oh yeah, it is known, 3.3 kilograms per second. Okay, so we can just solve it for A star being the area, cross-sectional area of the throat. Okay, let's have a look at everything here. 3 is the mass flow rate, R is the gas constant for air, TT is total temperature or stagnation temperature, and 0.685 is this constant, PT is the stagnation pressure, 200 kilopascals. So just solve this equation and you get an area equal to 8.3 times 10 to negative 3 square meters. Okay, now we can solve it for diameter. So we know that a circular area is equal to pi d squared over 4, okay, or pi d over 2 squared, same thing. And then, so replacing the values here, solving for the diameter. we get 0.103 meters or 10.3 centimeters. So that's the diameter of the throat. Okay, second part, the exit pressure can be calculated using the stagnation pressure formula, but this time we're going to solve it for that P here instead of for PT. We need here the Mach number at the exit, which was provided in the problem as 2.5. So you just need to rearrange and solve it for this PE value here. Okay. All right, so the pressure at exit is 11.7 kilopascals. That's less than the entry pressure, makes sense. The entry pressure, the fluid is at rest, and here it's flowing at a higher velocity, so therefore the pressure must be smaller. So it's 11.7 kilopascal compared to the entry pressure of 200 kilopascals. Okay, now part C, the exit temperature, just do the same thing, use the stagnation temperature formula, but you're going to solve it for the static temperature, which is this one. Sorry, this is called the actual temperature for the flowing fluid, which is at TE here. And this is the stagnation temperature, which is 500. So we rearrange this, use the Mach number here at the exit, which is 2.5. So Mach number goes here, total temperature here. Then you get 222 Kelvin. So temperature reduces at the exit. Okay, and exit velocity. You can, this is one is you can do it by applying the speed of sound ratio because we know the Mach number. We know that the Mach number is 2.5. Now we need to find the speed of sound. But note here that the temperature for the speed of sound at the exit needs to be the temperature of the exit, not the static temperature, the stagnation temperature, which is the one when the fluid was at rest. So 1.4 is the K value, R is the gas constant, and TE is the exit temperature calculated in the previous step. So the speed of sound is 298.7. Now we can find the velocity, because velocity is Mach times speed of sound. So velocity is 747 meters per second. Okay, so that's 2.5 times the speed of sound of that air at that temperature. And I think that's There's also exit diameter. The exit diameter is going to be, we know the throat diameter. Oh yeah, we know the throat diameter that we calculated before as a function of the mass flow rate. One of the, I think was the previous step, the first step. We know the Mach number at the exit, so we can find the area. So this is that formula that I presented before with the ratio between area at one section divided by the constriction area. This was also explained by Amir during the lecture. Have a look at the part in which he talks about the de Laval nozzle. So there's a lot of theory to be explained surrounding this system of compression, then a throat, and then expansion. Okay, so all these formulas are applicable to these designs. So the area at the exit is 21.9 times 10 to negative 3 square meters. Entry area, no. Oh, there is a constriction area. The constriction area is the A star. And there's no entry area in the calculations. So we start, the first part we start by finding the constriction area for that specific Mach number, which resulted for that specific stagnation pressure and total temperature. So then we found the size of the throat so that the fluid would be at speed of sound here at the throat. And here for the exit pressure, we only need to use the total pressure, which is like the maximum pressure achievable for this fluid. We use the maximum pressure or stagnation pressure formula and the Mach value. So again, in any point we need to use any area for this container here. We just use this area and this area here in our calculations. The exit temperature, again, is only a function of the total temperature and the Mach number. The exit velocity is a function of the speed of sound and the Mach value that is the requirement for our design. The design requires this Mach number, this Mach value, requires the air to be at this temperature. So the design here is to find the area, the sectional area of the throat and of this part here of this duct. So the exit diameter here is, so after finding the area here, you just solve for diameter. So that would be 16.7 centimeters for the exit diameter. So basically for this fluid, this air, in this condition here in this container, using a throat of that particular size that we calculated before, it would achieve the speed of sound here, and then it would achieve a Mach number of 2.5 in this section here with this design. Okay, Andrew, so that was the last problem. Do you have any questions? Okay, thank you so much. And good luck in your final examinations. So thanks for coming to the tutorials always. Okay, thank you. Have a good one.